So last time we talked about a construction which gave us the axiom of choice inside L. So that construction was one that depended very much on how we constructed L, right? We construct L in these slices where we use this definable power set operation at each stage. And it was because we use the definable power set operation that we actually get a nice well ordering of the whole universe of L. So you might think, okay, so we have this process which we run in V, which is, we assume is a model of our axioms. And okay, you've shown that you could then ask the question, what do we run the construction of L inside L? After all, the construction is about definite terms, which we can define in ZF or ZF minus. And it would make sense to ask, if I run the def operator inside the universe L, what will happen? So we could picture something like the following. So here we've had V like this. And we've cut out from V this possible inner cone L here. So the question I'm asking is, what if we run the construction of L? Of L inside the ZFC model L itself. After all, in L, I've got the ordinals, I've got all the axioms holding. I could start building up L relativized to L. What would happen? So that's relativized. The construction of L to L itself. So what would result? After all, we've got that this, given an alpha here, we decided to allow that this here was a definite function. So it's defined by definite recursion. And so it's absolutely definite. It's definite, it's absolute between transitive ZF minus models, right? Well, here are two, V and L itself. So it would look like that this function relativizes to L. Between V and L itself. I mean, indeed, this is the case, which we shall prove, right? Yeah. So this turns out to be the case. So what are we going to see today? So I relativize L alpha to L. This is just L alpha. So moreover, if I take the union of all of the L alphas constructed inside L or constructed outside, I get L. So I don't know whether that is surprising or otherwise, but in a sense, it kind of makes sense. Okay, let's try and make sense of that statement I just made. Okay, so I'm talking to section 4.3 in the notes here. So we start out first with a definition. So the axiom of constructability, it's called. This is more addressing the question of whether these two cones can be the same. Can L be the same as V? We've drawn it suggestively that it's an inner model of V, a proper inner model of V. For L to equal V, the definable power set operation would have to pick up all the sets of the universe. I mean, yeah, I'll say some more about that later. So the definition here is, so the axiom of constructability says every set is constructible. So, as in the diagram above, we assert that V equals L. And actually what that abbreviates is the more correct mathematical statement that for every x, there is an alpha such that x is in L alpha. So what we're saying is for every set x in the universe V, it appears at some stage in the L hierarchy. So this would collapse then V to L, right? Because any set here in V actually sits inside some L alpha. So V will be a subclass of L. Now it's called, in early days, people said, oh, let's adopt the axiom of constructability. It gives us such a nice picture of the universe. But logicians and set theorists, they don't actually think, I mean, despite calling it an axiom, they don't think of this actually as being an axiom that's true of the universe V. It's somehow too restrictive. I mean, you could ask the question, does V equals L? So set theorists tend not to adopt this axiom. And you might ask why. So the feeling is that you've got this logical operation the def operator. And the def operator here is tied in with notions of syntax, of language, semantics, when you talk about definability over a structure. On the other hand, the full power set operation is completely broad. It's defined not in logical terms, using logic of languages, but it's in more mathematical terms. It says just take all the subsets of a given set. So as opposed to the mathematical operation, which is of a set going to its full power set. Of taking all subsets of X. Definable or not. Definable somewhere or not. So this does not, the axiom of constructability does not have the status, I think, in set theorists' minds that the other axioms do. Okay, but that's something that's there for discussion. So let's move to lemma 412. So this is about the absoluteness that I mentioned of the L alpha function. So I suppose that W is a transitive class term. So it's giving me a collection of sets that's transitive. I don't say proper class, right? W could be a set. But as usual, we're supposing ZF minus holds relativized to W here. Then I relativize the construction of L to W. And what I get is all of L if W contains all the ordinals. Otherwise, I get only as many levels of L as there are ordinals in W. So V may be here with all the ordinals. And L, in the sense of W, depends on how big W is. W may only have height theta. But then the lemma says, if I run the L construction inside W, I get as many levels of L as there are ordinals in W. So L in the sense of W would be just this much. There. And the lemma is saying the construction inside W picks up the true levels of the L hierarchy. The second part of the lemma just says, I don't need all of ZF minus to get this argument to work. All I need is just a finite collection of axioms holding relativized to W. So there's a finite conjunction of ZF minus axioms. Sigma 1, right, I thought I gave it a name. This isn't a standard notation, this is just my calling it that here. So that in 1, I can replace the requirement that ZF minus holds in W by sigma 1 holding in W. And the conclusion is the same. So the usefulness of this will appear later. But what it's saying is that this ZF minus, which is an infinite set of axioms, remember all those foundation schemes and separation schemes and so on. Here we can actually replace that with a finite set, sigma 1, for this particular result here. Okay, I don't know if there are any questions about the setup. Okay, so over the page. So the first point to note is that this we decided is a definite function. And hence is, I'm repeating something in my introduction here, hence is absolutely definite. And hence is absolute for W. So another way of saying this is this function here is the same as the function defined relativized to W. So second note is, as ZF minus proves there is no largest ordinal. I can always add 1 to any ordinal and get a bigger one. We have that the ordinals in W, okay, so it's the ordinals in the sense of W, is theta, and this is a limit ordinal. That's what I'm saying here, is that this is a limit ordinal. We've already seen that being an ordinal is AD, so that's absolute between W and V here. So we're saying that for all alpha less than theta, L alpha is the same as L alpha in W, which is another way of saying this thing here in my brackets. So now we just write down this definition here, right? So this holds if the ordinals intersect W is an ordinal. It may have all the ordinals, in which case there's no theta that we're talking about. So L, in the sense of W, well, L is the union of the L alphas. So here I've only replaced L with its definition here. So this is a definite operation inside a transitive ZF minus model. So this actually gives us this. So I don't need the bracket. Right, so we take the union of this term here, relativized to W. This is the union of the relativized L alphas for the alphas that are in ON in the sense of W. By the line here, I'll just get rid of this W that's here. Being an ordinal is absolute to W, so this is just the alphas that are in ON intersect W. So now it's just the two cases of the lemma, depending on how many ordinals there are. So this equals L if ON intersect W equals ON, and it equals L theta if ON intersect W is theta. Okay, so that's the lemma here, part one. Okay, are there any questions? Then there. So, yeah, the maxim is for transitive ZF minus models, we can just run the construction of L inside them and we pick up L as far as we can, as far as there are ordinals. Now, what about then part two? Okay, so for in part two, it asks for a finite conjunction of ZF minus axioms. Well, you could ask, well, please write down this list of axioms, but this will be a rather tedious task, actually. The axioms that we need are the ones precisely to prove that the def function is absolute. So the function from alpha to L alpha is an absolute function, absolutely definite function. Right? So if you were to ask me to actually write down what the axiom sigma 1 is, I'd have to go back through the course and just look at which axioms I need, which instance of those axiom schemes I need to prove precisely that the def function is absolute. So, and this will probably not be terribly illuminating, right? But it's, I mean, in theory, possible. Right? So we'll just kind of buy to on that kind of assumption that one could, in theory, go back and write down and collect together those axioms. Or the other thing you could just simply say is, it may feel like I've been talking at you for an eternity, but actually I've only been talking to you for sort of 8 weeks, right? And I've only said a finite number of things. So I've only used in all of my lectures finitely many axioms so far. I mean, we've had theorems like the reflection theorem that says, you know, for any axiom we could do this, or there is a ZF proof that something reflects. Right? But when now I'm actually doing constructions, I'm only just using a finite number of axioms because I've only lived finitely long, right? So you could just let sigma 1 be in part 2, the finite conjunction of everything that I've said, every axiom that I've mentioned used in our constructions in the term to date. So the point is there is a sigma 1, whatever it is, and we don't really need to specify it precisely. So I'm just going to leave 2 as just saying that, right? We just let sigma 1 be a sufficiently large collection of axioms, but finite, and let sigma 1 be their conjunction. Right? So I just leave that as kind of something that's plausible here. So for 2, sigma 1 is the conjunction of sufficiently many axioms of ZF minus to prove that this function here is definite. We also use the fact that there was no largest ordinal to say that W had a limit ordinal height. Wasn't necessary, but we could, it's just convenient to do that. So, okay, let's probably from sigma 1, I can already prove that there's no largest ordinal, but let's add it in just to make sure. Plus axioms proving there is no largest ordinal. So then if everything there in sigma 1 is true in W has no largest ordinal. Then it's a limit ordinal there. I mean, this is kind of a feature of proofs in general. A proof is only a finite object. It's just a finite number of lines in an argument. And only finitely many of those lines are then axioms that are used. So any proof only uses finitely many axioms at any one time. So that finishes 2 in the lemma. Again, I don't know if anyone wants to question or object to anything there. So the corollary then is, so it's proof in ZF that the axiom of constructability holds relativized to L. L thinks each of its sets is in some L alpha. So it thinks each of its sets are constructible. Well, it's transitive. It's certainly a model of all the ZF minus axioms. Here, so the lemma applies. What does it mean to relativize an equation? To say that two classes are equal. They're given by these terms, V and L. That's equivalent to saying that V in the sense of L is this term in the sense of L. This is a collection of sets inside this transitive collection. So it's this. Nothing special about L here. V in the sense of W is W for transitive ZF minus models W. Now, I apply the lemma with L as W. So I'm going to say here, V equals L equals L. Here, L in the sense of L here. Well, this is the level of as many levels of L as there are ordinals in L, which is all of them here. So L is L, right? So this is a tautology. These are obviously true, so this is true. So again, stop me if there's anything that's questionable here. So it looks like I maybe done some magic here, but actually all I've done is apply the lemma to work out what this is, right? The rest is just relativization of terms to other terms, right? That's just our relativization theory from chapter 1. Right? So this is our first relative consistency result. So we'll take a moment to say what this means. Right? What does con for theory T Con T is our kind of informal abbreviation for there's no proof of a contradiction from T. Meaning I can't have a proof from T. Here are my axioms T, and I have some proof down here, and I prove some statement chi, and I can also prove not chi. So it's impossible to prove from T a statement and its opposite. If we did, we would think the system was inconsistent. So con T says this: there's no proof of a contradiction here from T. Now, I mean, a proof, as you'll have learned from Gödel's incompleteness theorems, a proof can be mechanized, right? If the collection of axioms and the language is all computable, we can have a machine check a proof, right? So if you had a proof of a contradiction for some axioms, you could give that to the machine to check that was correct, right? That you had a proof chi and not chi. What you can't do necessarily is ask the machine, is this set of axioms given in some algorithmic way consistent? Because then you're asking the machine to verify all possible proofs. You're not giving it a purported proof of a contradiction and asking you to check it. You're asking the machine to go away and come back with an answer. And this is precisely the halting problem, which Turing showed was impossible. You can't ask a machine, a computer, to go away and say, are you going to halt on this program, which I'm going to program you with? So likewise, you can't get a machine to give directly a yes/no answer as to whether a system is consistent. Speaking kind of informally and roughly here. Of course, a machine might happen upon a proof of a contradiction quite quickly, and you might get an answer back before lunchtime, right? But on the other hand, you might not. It might be that the theory is consistent and the machine will never find a proof of a contradiction, but you'll never know it. What we have here in the statement of the theorem is, I mean, just in terms here, this is saying if this theory is consistent, then this theory is consistent. So to think of it in its contrapositive terms, right? If there's an inconsistency from this set of axioms, if I can prove a contradiction from these, some chi and not chi, then actually there's a contradiction here already in ZF without this extra axiom of constructability. So it would say, right, if you were talking to a mathematician and you were trying to urge them to accept the axiom V equals L, right, they might be resistant and they might say, well, why should I accept this axiom? Right? Maybe it introduces an inconsistency. Maybe I could start proving, 2 + 2 = 5, right? If I start adopting this axiom. Yeah. But then you can reply and you can say, no, in fact, this is a safe axiom to add to mathematics because adding it on doesn't introduce any more inconsistencies than there weren't there already. Because if there was an inconsistency here, this theorem shows there's an inconsistency already over here. we can't rule out inconsistencies of a theory within a theory by Gödel. We can go to a stronger theory than this and prove that it's consistent. And set theorists do that kind of thing all the time. The axioms of Peano arithmetic are a weaker set of axioms than ZF. We can't prove in Peano arithmetic that con PA, that Peano arithmetic is consistent. That's Gödel's result. But we can prove in ZF that PA is consistent. Because in fact, if you look at HF, admittedly this is a set theoretical structure with an epsilon on it. But we can define within HF here the natural numbers, the von Neumann naturals, and show that they are models of PA. So in set theory, we can prove that PA is consistent. We've just got that omega and 0 and plus times and the successor function and whatever else. This is a structure which is a set theoretic structure. And we can prove in set theory that this is a model of the Peano axioms. So if we go to a stronger theory, we can always prove the weaker theory is consistent, hopefully. But as I said, introducing V equals L as an axiom is a safe procedure, right? At least, right? You won't introduce a consistency that wasn't there already. So clearly this is of interest. Okay? So let's see how this goes here. So we prove the contrapositive. We suppose this is inconsistent. So in logical notation, we have from ZF plus V equals L, we can prove in first order logic, this is the symbol for prove in first order logic, some formula and its negation. This was the chi and the not chi I was talking about earlier. I mean, if we have separate proofs of phi and another proof of not chi, we just put them together and we have a proof of phi and not chi here. So what have we shown? We've shown in ZF, we laboriously went through all the axioms and showed all the ZF axioms held in L. Previous corollary just showed us that V equals L holds in L. So we have this here. So this is the last corollary and theorem 4.7. Now what I've got is I use, well, the Soundness Theorem from first order logic. If I can prove this from a theory, and I've got that this structure L is a model of the theory, then anything I can deduce from this is also true inside L. Sorry. a soundness theorem. 1 point something or other. I was about to say 1.x, but maybe 120, which just mentions that fact from logic here. Okay, and now on, it's just definition of relativization. It's all downhill. This is a conjunction. And this holds if and only if. This is the same. And now we've got not phi in L. So these are just definition of relativization. And then, hey presto, what have we got? We've got a proof in ZF of a statement and its negation. So ZF is inconsistent. Hence not con ZF here. So if you're a careful logician, you can work out that in fact, this argument is actually a number theoretic argument about code numbers and proofs and so forth. So actually this, if you ask me, what is this a theorem in? Is this a ZF theorem itself? I'd say no. Actually, it's a theorem just in arithmetic. It's a theorem in piano arithmetic. That any consistency like this can be reduced to a consistency there. But don't worry about that. That's not the point. The point was that we don't get any extra inconsistencies. Okay, so just to finish by some, so Paul Cohen in 62 just to round the story off, he showed that con ZF implied that it was consistent that we would have ZF and V is not L. So this was the first point, right, where we had some view as to how, or some insight, or some hint that perhaps V could not be L. V does not have to be L. Right? It's consistent. We could add the statement V is not L to our axioms, and again, we don't introduce any inconsistency right here. But this was done using entirely different methods. Which would be a subject of, well, the next course, if there was to be a next course. It would be a course on forcing. Sorry, that's F-O-R-C-I-N-G. So this is the forcing method here, which he devised and to show this. So forcing is much used by set theorists today. There's a very elaborate literature on these kind of forcing constructions to prove these kind of relative consistency results. So this kind of thing is called a relative consistency result. And a lot of set theorists are involved in producing relative consistency results of different theories here. So his same method, and we'll see con ZF plus con ZF, sorry, implies con ZF plus the negation of the axiom of choice. We'll talk more about this one next time.